Good morning and welcome to session 2 of CEWIT2021, day 2. We'll be talking today about blockchain and AI. Our first presentation is by Mengqian Zhang. Mengqian Zhang is a fourth-year PhD student in the Department of Computer Science at Shanghai Jiao Tong University, Shanghai. She received her BE degree in computer science from Ocean University in China, and since July of 2019 has been a visiting scholar at the Centers of Frontiers of Computing Studies at Peking University. She'll be talking about blockchain and algorithmic game theory. Ms. Zhang.
Oh, yes. Thanks for a nice introduction, and I will share my screen. Okay. Hi, ladies and gentlemen. I'm Mengqian Zhang from Shanghai Jiao Tong University, and I'm honored to have the chance attending CEWIT2021 as a speaker. Today, I will present our work, Accelerating Transactions Relay in Blockchain Networks by Reputation. To start with, I will give a brief introduction on blockchain. Blockchain is a chain of blocks containing transactions. And in blockchain, the transaction indicates the state transition. For example, in the pioneering Bitcoin system, a transaction is the transfer of assets from one address to another. These transactions will be organized as a block by several special nodes called miners. The miners will compete to generate a block for some rewards, and this block generation process is also known as mining. For this newly generated block, by containing the hash value of previous block, it will be appended to the chain. Then the whole chain as a ledger will record what has happened in the system. Everyone, not only the miners, could keep a copy of the ledger, so there is no need for any centralized entity. In addition, the mining process and the hash chaining of blocks make it extremely hard to modify the blockchain history. So although there is no centralized entity, the security can be assured. In this kind of system, a transaction will go through several steps before the final confirmation. First, the user who creates the transaction should also sign. Then the transaction will be broadcast across the whole network by some relay nodes. After receiving a new transaction, the miner should verify it carefully, and if the transaction is valid, it will be put into a local mempool. Then this transaction will have some probability to be included into a mined block. After the block is broadcast and further accepted, this transaction is really done. This work will focus on the transmission of transactions, which lays the important foundation of the whole system. This transmission occurs in the network layer, which is a permissionless and anonymous peer-to-peer network. Anyone can join in the network. For the new participant, it can find the existing nodes from the hard-coded SYN node or ask the peer for further addresses. They will actively make outgoing connections and also accept the incoming connections. After connected, they can work as a relay node. For the relay nodes in the network layer, the critical task is to provide a fast delivery of data. It will help the transactions to be received and further processed by miners as fast as possible. To achieve this, the relay nodes are expected to behave well, include to forward valid transactions and respond to the data requests from neighbors. However, the network's permissionless and anonymous environment open the door to the selfish or even malicious behavior. Here, I focus on two misbehavior, which are closely related to the data transmission, namely the unreliable and the inactive behavior. First is the unreliable behavior. That is, the node may send invalid transactions across the network. Here are two possible cases. One is that the node is exactly the original generator, For example, it may generate a lot of invalid transactions to launch the denial of service attack. The other possible case is the node just carelessly forward the transaction from neighbors without any verification. But whatever the reason, this unreliable behavior will lead to a further spread of the invalid data. As mentioned before, the miners will check them carefully before the mining. So these invalid transactions will not be included into a valid block. However, their spread will waste the node's computational resources and weaken the network's ability to serve the valid data. The second is the inactive behavior. That is, the node may behave inactively when forwarding data and responding to the data requests. There are also two possible reasons. One is that the node just refused to provide service purposely. A previous work has indicated that current blockchain design provide no incentive for nodes to broadcast the data they have known. The other possible reason is the node is just restricted to some objective conditions, such as the distance, local bandwidth, and so on. Whether on purpose or not, this inactive behavior will delay the ongoing data transmission, so it should be detected and further solved. Current blockchain system, especially the cryptocurrencies like Bitcoin, take a simple strategy. All nodes exchange data by flooding. It contains two steps. First, everyone should verify each received data carefully. It's mainly to fill out the invalid transactions in time. Then forward the valid data to all outgoing neighbors. This action differentiates the ingoing and outgoing neighbor. It's mainly based on the condition of the consideration that the proactively connected neighbors are more likely to behave well. However, this assumption is not really reasonable. More worstly, this simple design has several drawbacks. In the verification process, it requires everyone to check to check the same transaction repeatedly. It's really wasteful and slow down the transmission. For the nodes for the user who creates the transaction, they respect the low latency and prefer to skip the verification process. It has long been a research challenge to balance well the DOS prevention and the non-verification requirement. Then for the forwarding process, it gives the inactive neighbor the same chance to be the receiver. However, as we discussed before, the inactive neighbor provides no help for further transmission. So to some degree, the currently used protocol is inefficient and goes against the network's the critical task of the network. So it motivates us to think how to accelerate the spread of transactions without going through the quality of service. Previously, here are some work focusing on the transmission of transactions. In 2013, a paper suggests to increase the connectivity for speeding up the transmission. However, it brings huge overheads on the bandwidth. A later work proposed a solution to reduce the bandwidth for propagation. However, it requires close cooperation among peers, which is not practical. Other solutions include the topology-based routing and feedback-based approach, but they all bring new risks of some attacks. We solve this problem by introducing the concept of reputation. Here I give an overview of our solution. First, we design a reputation mechanism to distinguish the different types of neighbors. Then we propose a reputation-based relay protocol called Repulay. It accelerates the transmission by optimizing the verification and forwarding process respectively. Intuitively, in the first step, we should only focus on the transaction from the unreliable neighbor because they are more likely to be invalid. And in the second step, we should avoid the inactive neighbor because they provide no help for the further transmission. In detail, the term of reputation in our mechanism represents the node's credibility. And everyone could calculate the neighbor's reputation based on their historical behavior. In our design, the reputation is a local value, and it means different people may rate the same node differently. And the reputation is a tuple consisting of two values, R1 and R2. Both values can be positive, 0, or negative. And these two values correspond to the two factors we care about, namely the quality and the quantity of data interactions. For the first value, R1, its computation relies on a design called sliding window. Everyone in the system should maintain a window for each neighbor. For example, for the node A here, it has k neighbors, so it should maintain k windows simultaneously, and the size of each window is k. When receiving a transaction from neighbor I, if the transaction is valid, the node A will record a positive one in the latest box of the neighbor I. And on the contrary, if the transaction is invalid, a negative one will be recorded. In this way, the neighbor I's R1 is exactly the sum of all records in this window. Then for the neighbor who sends invalid transactions with frequency Q, in expectation, its R1 will be stable at 1 minus 2Q times W. Recalling that the unreliable nodes will send the invalid transactions frequently, then the R1 will be quite small, so R1 could help us to tell apart the unreliable behavior. For the second value, R2, it focuses on the quantity of data interaction. Here we use Fi to represent the number of useful transactions that we receive from the neighbor I, and we call a transaction useful if it's valid and we receive it for the first time. Also, we use Ti to represent the number of transactions that the neighbor I that we provide to neighbor I. Then R2 is designed as Fi minus Ti. In other words, R2 is the net number of transactions between the node and its neighbor I. Intuitively, for the inactive neighbors, they just receive data and don't provide the data to us, so their R2 will be quite small. Then this value will help us to find the inactive behavior. Based on this reputation design, we propose a relay protocol called Relay. Relay adopts the probabilistic strategy to process the transaction. Here are two questions to answer. Namely, whether to verify a received transaction and then select which neighbor as the receiver. To answer these two questions, we designed two probability functions. In the verification process, after receiving a new transaction, we will verify it with a certain probability PV. The PV is deduced from the sender's R1. If the sender's window is not full, we will set PV as 1. Namely, we will check the transaction definitely because we don't have enough historical records and we cannot judge, we cannot decide whether the sender is malicious or honest. Else, if the sender's window has been full, we will set PV as the larger value between alpha and 1 minus eta over Q. Here Q is the sender's error frequency. It is estimated by the sender's R1. And the alpha is the minimum check probability. That is, even if the sender looks like an honest node, we still check the transaction with a probability alpha. The other parameter eta is a maximum error frequency that the system could tolerate. And by designing the probability function like this, we prove that by verifying the transaction with a probability no less than 1 minus eta or q, the node's error probability will not exceed eta. It guarantees the quality of service in our protocol. Then in the forwarding process, each neighbor will have some chance to be chosen as a receiver. Here is the probability function. It contains two parts. The first part is related to the neighbor's R2. A high R2 means that the neighbor has enough computational resources to forward data and is also willing to do so. So this part makes the neighbor with high R2 are more likely to be chosen. The second part is for fairness. It gives the newly connected neighbor some chance to be chosen. Okay, in order to evaluate our design, we conduct a several simulation based on a network with 1,000 nodes. And this slide summarizes the main parameters involved in our simulation. The first simulation focuses on the transmission speed. We compare our design rapidly with the widely adopted protocol Bitcoin float. As the we use the time slots to spend transaction as the metric. Take the rightmost two marker as an example. In order to spread the transactions to 90% of nodes, the Bitcoin float will take about 247 time slots, while our Rapulate only needs 117 time slots. It supposes that Rapulate can effectively accelerate the spread of transactions. And in the second simulation, we integrate Arnold's local reputation list. Here, the x-axis is the node's ID, and the first 70% are honest nodes, and the others are unreliable nodes. The y-axis is the first value of reputation R1. The figure shows R1 can help us to distinguish the unreliable nodes. And their R1 are quite small. Similarly, we could use R2 to distinguish the inactive nodes. And we also realize the average accuracy and verification rate. An important observation is that only verifying about 50% of transactions can permit accuracy above 0.9. It means although we don't verify much transactions during the process, the accuracy can be guaranteed, and we don't miss too much invalid data. Okay, at last, I'd like to conclude this presentation. First, this work focuses on the network layer of the blockchain, and we design a reputation mechanism to distinguish different types in the network layer. You could find there are it's about three behavior: the honest behavior, the inactive behavior, and the unreliable behavior. Then, based on this reputation mechanism, we propose a relay protocol called the Rapulate. The Rapulate adopts probabilistic strategy to process transaction. And it's very important that in our design, reputation is a local value, and each node just make a decision independently. But as a whole, They successfully accelerate the spread of transactions and improve the system's performance. This feature fits well with the decentralization of the blockchain, and I think this is the most important thing I want to say. Okay, that's all. Thank you. Thanks very much for the kind attention.
Thank you very much, Ms. Zhang. It's a very interesting presentation. There are no questions in the Q&A. However, I have one myself. Do you see any effect on, you've used 1,000 nodes. Do you see any effect or any results from a larger number of nodes?
Sorry?
As the number of nodes increases, do you see a benefit?
Okay, this is a good question. I think this design is independent with the number of nodes because whatever the number of neighbors, we can score them use this mechanism, and it is only based on the data interaction between the nodes. So. But it is reasonable to do more simulation or do more research about the dynamic environment.
Okay, thank you very much for a very interesting talk. Our next speaker is Bruce Swett. Bruce Swett is Chief Artificial Intelligence Architect with the Mission Systems Sector of Northrop Grumman. He which is a provider of security systems and solutions. He did his PhD in neuroscience and cognitive sciences at the University of Maryland, College Park. Did his postdoctoral studies at the National Institute of Deafness and Communication Disorders at the National Institutes of Health. His experimental computational research focuses on high-performance computing to understand how the brain learns and automates sequences. Dr. Swett, the floor is yours.
Fantastic. Thank you very much for this opportunity to present. And we'll be discussing today responsible artificial intelligence, or RAI, and specifically around policy requirements and contracting implications. And this is work that I've done in collaboration with Carl Hahn, who's our Chief Compliance Officer at Northrop Grumman, and really addresses a lot of the challenges we have in the fielding of artificial intelligence systems. So our outline for today is that we're going to talk about AI trends and why should we care about this. Also, some of the challenges that we see with artificial intelligence, and then how do we actually address these challenges in meaningful ways so that we're ensured, we have justifiable confidence that artificial intelligence is being used in responsible and ethical ways. Also, the need to build a multi-stakeholder collaboration environment. We'll talk about that quite a bit. Some suggested policies for the US government, just as a starting point. We'll also look at responsible AI governance throughout the AI lifecycle and point out really how artificial intelligence is different than other software acquisitions. And then on contracting, sustainment, and intellectual property, or IP, and how that differs with AI and what the implications of responsible AI or RAI are. And we'll have the beginnings of a proposed RAI contracting framework. So we've seen really in the last 10 to 12 years this trend where artificial intelligence has demonstrated again and again the ability to have superhuman performance in very narrow specific areas. That largely has been in the world of games, things like video games like Qbert, or board games like Go or chess or shogi. But then more recently has branched out into strategy games like StarCraft 2, and even real-world military simulations like DARPA's Alpha Dogfight trials, where an AI agent beat a trained F-16 pilot 5-0 in a very limited guns-only air dogfighting application. So we're seeing that artificial intelligence can do really tremendous things in narrow applications, but yet at the same time that all of that promise of what we can do with artificial intelligence is really tempered by the challenges that are concomitant with using artificial intelligence in real world systems. And those have been, I think, well documented, things around data bias, around adversarial AI attacks, attacks to basically every part of, from training data to models to trust to comms to hardware to all of these different areas are really part of a landscape where artificial intelligence can be attacked and degraded or manipulated. So if we're going to do responsible artificial intelligence, or AI, how are we going to address these areas? And a lot of academic organizations and companies have been taking pieces of this because this is very complicated. So there's a number of areas around say the different types of data bias and how we can identify those and how we can mitigate those throughout the process. But there's really not a holistic approach to all of this to have responsible AI governance throughout the AI lifecycle. So we think about it in kind of 3 layers, and it's this kind of holistic approach. The first question is, what's ready? When is AI good enough to be used in systems? And how does the US government create policies and contractual requirements that ensures that the application of artificial intelligence is safe and effective and monitored from beginning to end? So that has to be defined, and we'll give some kind of really entry-level rules or thoughts for what those requirements could be. And those then need to be flowed into contract requirements, but also corporations are going to have their own policies in order to mitigate risk and rules about how AI needs to be developed, fielded, monitored, and governed. So I think there's going to be 2 sides of this coin. One's going to be on the corporate side, one's going to be on the government side, and we really need to bring those parties together. So when you identify what ready means, you have to look at what the AI is intended to do and how effective or how much risk is engendered by its appropriate use. But what if it's misused? What if it doesn't match the data, or if the feature distributions within the data drift, or someone just decides it's a good idea to use it for something else without actually going through this RAI governance process? So we need to have kind of a risk characterization about the appropriate and inappropriate or unintended uses of artificial intelligence models and systems. Now, this concept of what is ready, what is justifiable competence, in the words of the National Security Commission on Artificial Intelligence, drives a set of tests and processes that provide evidence. So we say, what is ready? And then we have to go and find out if our system is ready or not. And that's the second part of this, where we say, all right, we now need to collect evidence, especially military or government uses of artificial intelligence often are legal processes, and we need to capture this evidence and store it in an immutable audit trail so that we know whether we're doing the right things or not. We talked a bit about data bias. Is it secure and unbiased? Are the models performing and appropriate to the data? Are they secure against cyber and AI attacks? Are they operationally evident and explainable? Are the process and decision records kept? So who decided what when? And do we know those things? Are there kind of trace back and accountability features? And then are there controls for both appropriate use and also unintended effects, including graceful termination? All right, well, now this starts to look like something we can go out and code to. We can create processes that collect this evidence and run these tests and allow us to then say, all right, we're supposed to do this. Maybe one of the policy and the threshold in the requirement says your data must be 98% free of bias. So we run the test and we find out that our data for the AI model we're training is 82% free of bias. And so it fails. And that means now we can quantify that, go back and fix it, and then come back and retest until we meet the thresholds. So collecting evidence is critical. And that leads to the ability to actually monitor for compliance in real time, to be able to say, all right, we know what the policies are, the thou shalts, we know what we're doing, which is the data, and now we can analyze and look at the evidence to say, we know what the data test results are, performance of the models, the security results, effectiveness, explainability, who did what, where, and what decisions were made. Also, it's good to realize and to remember AI is software, but it also lives on hardware and connects to networks. So those have to be secure as well. The control status of graceful termination are in place. And then we can look at the comparison with the policy thresholds, like the data bias analysis example I gave, and then you'll know at any given time whether your AI systems are safe, ethical, reliable, robust, if you have justifiable confidence for responsible AI. So this is what we mean by RAI governance, and it's one of those things that you don't just do once, because, as I'd like to say, AI is never done. There's always another data set that you want to update it with, and that means you have to retrain, it means you have to retest, you have to recollect all this evidence, and you have to then do compliance monitoring on the updated version. It changes a lot of things in the relationship between the government and those companies, organizations that build artificial intelligence, and we're going to talk about that in just a second. So because AI is never done, we have to automate these processes. You can't have manual processes that take 6 months to do. This needs to be something that's done every time we rebuild, and that gives us a repeatable, data-driven process that's evidential, and then provides the audit trail to make sure that we're doing what we're supposed to be doing. So given that kind of construct about responsible AI, well, let's talk about how artificial intelligence is different from other types of software. And the challenges that brings means that we have to have a closer relationship between the US government stakeholders and AI vendors, but it also is another dimension around non-technical stakeholders, which may be program managers, may be contractual people, legal people, compliance people, and technology developers who live in very different worlds and speak very different languages. So the policy developers, this is kind of the top-down signal that says, okay, your data should be 98% free of bias, and that becomes a requirement that it has dictates what evidence and what tests you run and the thresholds for that. But there's also another side, which is that AI architects and developers and subject matter experts learn new things about the best practices for AI applications all the time. So there's also a bottom-up signal about here are the best things that we need to do, and codifying that. And then also, this is the evidence we should collect even beyond the requirements, and that may inform best practices and updating those requirements. So you have that from the bottom up, those automated RAI tests that go into immutable log. And then you have this middle piece, which brings them all together. So you don't have to be a technical specialist in artificial intelligence to look at the governance dashboard and say, yes, you were required to test for data bias, 98%, yours came in at 82%, so you failed that, which means you need to go back and fix it. Well, that's great. So that helps people who are the PMs, legal, test evaluation, and audit folks who may not know all of the math or the programming or the back end to understand that, whether something is usable or not, and whether we have justified confidence across a whole range of tests, and those tests are going to evolve as AI evolves. So this helps both sides. It helps the government stakeholders to understand what's going on. It also helps the AI vendors who also have program managers, legal teams, test evaluation, and audit personnel, so they can kind of meet in this middle space to say, all right, maybe a company has 5,000 AI models in 300 systems, and you should be able to know at any given time which ones we have justified confidence in from an RAI perspective. So in this way, you've got the required tests come from the compliance and from what the contract says to do, and that drives our evidence collection. And then our evidence collection are the test results that feed into the compliance in this RAI governance dashboard. So we believe that this is a really powerful construct for enacting things like the DoD 5 ethical principles, is to say, well, how do I actually do this? Well, I have to have requirements, I have to have evidence, and then I have to have RAI governance in real time for everything the US government uses. So I think that this construct will help us to create this multi-stakeholder collaborative environment and ecosystem. So then, what does a policy look like? I've talked about the training data as biased, and we kind of went backwards. We went from known vulnerabilities and said, we know AI has challenges with these things, and we walked backwards to say, well, the US government should issue contracts with requirements that close these vulnerabilities. So those things, training data, the AI model being misused, and so it adds risk, that doesn't perform, its performance envelope is unknown. This is a big one because a lot of the neural networks, convolutional neural networks, operate in a very high dimensional state space. And so it's hard to know if the environmental conditions change. So say I'm trying to find a truck using video, and I've trained it on certain data and it performs at 99.9, it's doing great. But if the data that comes in after I've trained it is different, maybe it has a different look angle, maybe different atmospheric haze, different pixels on target, well, does it degrade gracefully? Does it go from 99.9 to 96? Or does it go from 99.9 to 10? Well, that's catastrophic failure. So we need to be able to characterize when we should use which algorithms and which models. So eventually we'll probably have hot swapping between ensembles, and that's great, but we can't do any of that if we don't know where they're going to work and where they're going to fail and how they're going to fail. So we also have to have operational effectiveness testing to make sure it's doing what we expect it to do, and then security for cyber attacks, adversarial AI attacks. Human understandability is huge, and a lot of work has been done in recent years. So making sure that users understand how the AI got to the results it did, and human understandable and explainable, and then securing AI hardware and network. So you say, okay, well, those are not bad, right? Those are some of the things we know are problems or challenges. The US government could set this as a basic set of requirements, and then you could inherit and specify, more detailed ones for use cases or contracts. But this then says, oh, I've got certain evidence that I can collect the evidence to see if I meet the US requirement. I can create an immutable log that gives provenance around who did the tests and when, and then I can at any given time know whether my system is trustworthy and responsible in an RAI kind of fashion. So this then is the flow from the government's requirements to what we collect to the immutable log to real-time AI governance. And responsible AI governance is going to be done all over the place. It's going to be done on the government side to ensure they're getting what they purchased. It's going to be done on the vendor side to ensure that we met our requirements and did what we're supposed to do. There's going to, to make sure that we are that we've really checked all the boxes from a legal perspective and a compliance perspective. So then the other piece that's really important here is that responsible AI doesn't end when you give something to the government. And this is really one of the biggest challenges for responsible AI, is that normally, the government says, I want this thing, vendor says, I've built this thing, here it is, and you throw it over the fence, they do some testing, and the relationship is over. That is not true because AI is never done. So, in this case, you have some mission requirements and say we have those policies I just talked about. You have a development tool that automatically tests and collects evidence with best practices. And so I get not just a trained AI model, but I get a trained and RAI secure AI model. All right, well, that's kind of cool. And then from there, I deploy it to some hardware, and maybe I get a better sensor performance. This is a radar, but it could be anything. And you can see there's the data streams in the real world are probably different than the training streams, the data streams I use to train it. So normally that's kind of how software works, but with AI, you have to continuously monitor and update to make sure that it's still safe, secure, and that we're confident that it's doing what it's supposed to, which means I've got to monitor it periodically and then decide, is it still working? Is it still safe, secure? Is the data biased now? Is it drifted? Does it need to be retrained or retested? And if I retrain it, I've got to go through those automated tests again and then redeploy it. So this is a very, very different relationship between the US government in purchasing things and the AI vendor that is developing AI, because they're going to have to stay coupled and connected for a long, long time throughout the process. And then, so in thinking of this as an iterative, ongoing assessment and governance of artificial intelligence models and systems for every time we use it, that's a really huge deal. So now we're going to change gears a little bit, and we're going to talk about, well, what are some of the contracting, sustainment, and IP implications of this? And this is Carl Hahn's work, is to say, well, contracting then and the specifications and standards for performance and operation are really different for artificial intelligence, and there are different risks. And then what's the risk allocation? So are organizations indemnified? Are there some bounds on that liability? Because we want to, of course, identify bad actors, but there's also inherent risks as we're going through the learning process of creating AI systems that we can use for government purposes. How do we manage that risk, and what are the limits of those liabilities and the disclaimers on that? The other then is beholden on the vendors, the companies that are creating AI, to say this is what this AI model or system is good for this thing within this performance characterization bubble. And if you use it in here, then that's acceptable use. But then if you take it and you put it over here, you're going to have to retrain and retest and revalidate that so that it helps identify risk for unintended use and some latent defect that we didn't know about because we were intending it to be used for a different application. So that kind of warranty, again, is a way to kind of parse the risk landscape from a legal and contracting point of view. And then, from a products liability lens, did you do some level of no-fault pooling, or how do you allow companies to explore and develop and mature in this space without crippling them with some level of overburdened risk allocation? Now, we talked a little bit about sustainment, is that this has implications because artificial intelligence models, the data is a part of the process, and that's very different than other kinds of systems, which means if company A develops an AI model on their own data and then sells it to a government customer, the government customer uses on a different data set, it may have very, very different performance. And if the government customer owns the data or says, you have to use this data and the data is bad, how does that risk allocation, how is that managed from both a contracting point of view, but also it's the sustainment that this is an evolving dynamic operational environment, which means that the performance requirements are going to change and evolve, and that the data that's used for training and the algorithms are all going to change over time, which means that the sustainment tail for responsible AI is much different than just the normal kind of handoff for testing. So continuous monitoring, these feedback loops, lots of root cause analysis, which is why you need the immutable log and the provenance journal and the auditing using the RAI governance system. Intellectual property is challenging because now we have another factor. It's not just the algorithm, but it's also data provenance and ownership, and that is it customer data? Is it third-party data? Do you have a choice in the data that you're using? What if that degrades the performance of your algorithm? Or if you need that data as a contractor or a company, do you have access to that and use rights in the same way you might have with software? So that those kinds of data rights are an important piece. So there's then not only the algorithm and the model and the data, but all of the different pieces of who owns what and under what use cases you can use that IP. So there's also a more forward-looking thing, is that as AI is used to develop and design new systems, there's certain reinforcement learning. You could say, I'm going to design a new chip, computer chip, and it's the AI that really has designed it. Well, that raises new issues. So if company A provides that capability, company B, does company A own the IP that was produced by the AI, or is that has to be really clarified in contracting? If company B may want to have sole IP rights over that when they purchase it. So those are really interesting, challenging questions. And so in thinking about, where do we go from here, that in thinking about our responsible AI contracting framework, the collaboration between policymakers industry on those standards and requirements is critical. We put down 10 just to start with, but that's a different kind of ongoing relationship. It's going to have to be flexible and agile in a way that's never really been done before. There's going to have to be safe harbors respect to risk allocation so that we can mature enough to be effective and to really address these challenges for responsible AI. And then we're going to have to mitigate risk, whether it's by pooling or some fault-based liability. And then that IP rights piece and extending that to data and algorithms and combinations becomes really, really critical. So the summary as we're wrapping up is that AI has incredible potential for game-changing impact across all sorts of applications for the US government and commercial industry. It also has very significant challenges, and as evidenced by the dictates on the 5 ethical principles and responsible AI. We believe that RAI governance has these 3 fundamental elements, which are US government and corporate policies, this automated AI testing and evidence collection, and then compliance monitoring, which we call RAI governance writ large. And so I think that this gives us a framework for how to do responsible AI governance for US government applications. We do believe that this multi-stakeholder collaboration environment is essential across technologists and non-technologists and across government and vendors. And then there are a bunch of legal dilemmas for contracting, sustainment, and intellectual property that really have to be addressed. And we've offered kind of the beginning thoughts of a legal framework for that. So that is the end of the prepared discussion, and I'm glad to take questions.
Thank you, Dr. Swett. That was a very, very detailed discussion. We have no questions in the Q&A, but I have 2 of my own. You mentioned an immutable audit log, and I assume that is some sort of blockchain implementation.
Panel, let's see. I think, Arnold, are these questions for me in Q&A?
Yes, there are no questions, but I'm asking one.
Okay. Yes.
Right, your immutable audit log, I assume, is a blockchain implementation of some sort?
Could be. There are a number of different forms. Blockchain is probably the most secure, correct.
So the second question I have is that, we read recently that Facebook has just deleted all of its facial recognition data due to some unforeseen and foreseen risks that they might encounter. Would you support an open source data collection so that people could actually audit, an open source community could audit, or would you support sequestering data as Facebook did?
Well, I think we're into issues of data privacy and protection and transparency, and I think I can't speak to the Facebook issue directly, but I do think that people having transparent understanding of where their data is and who's using it and how to decide whether, as the European Union has codified in their language, is really critical. And I think that government applications of this, there are a lot of landmines like the one that Facebook ran into. But I think that by having a clear use case, risk description, and RAI governance practice, you can really mitigate a lot of those.
Okay, thank you very much.
Sure.
Our next speaker, we're going to be a little bit, Dr. Dou is here. Okay, we've had a little bit of a delay. Our next speaker is Dr. Wenwen Dou, currently Associate Professor at the College of Computing Informatics at the University of North Carolina at Charlotte. Her main research interests are in visual analytics and text mining and computer-human interaction. She has worked at the Pacific Northwest Laboratory, U.S. Research Office, U.S. Special Operations Command, National Science Foundation, and the U.S. Army Engineering Research and Development Center, and at Lowe's. Welcome, Dr. Dou.
Hi, good morning, everybody. I'm very happy to be here. Thank you for the introduction. Let me share my screen so we can get started right away. Hopefully you can see my slides. slides. Let me know if you can. I'm happy to be here to share my research and also applied work on interactive visual analysis and its kind of practical applications. Oops, I guess I deleted. So we have, as we speak, right, we have more textual data. So my research is mostly focused on visualizing textual data. So if you think about Tableau, that's across the board, everybody is using to analyze, to visualize data, but Tableau mostly applies to non-textual or tabular form. But what if we want to extract information and patterns from textual data? Sometimes we call it unstructured. It requires a whole different set of analysis methods with different sets of machine learning algorithms. So, and then text data is actually everywhere. As we speak, more emails are being sent, social media posts are being generated, and scripts on YouTube, so on and so forth. Almost many data sources you can think of contains text. And here are some of the just the kind of the big categories of textual data. So we have social media, we have news, and in different organizations, we also have reports and also books. So all of these, the data contains a lot of important information. So what can we do with social media data? So you can certainly use it for marketing, for promotion. That's very standard in industry. But in terms of research, what we have done, let me give you an example of what we have done with social media data is we use it to understand large-scale social phenomena, like the Occupy Wall Street, for example. So it's a year-long movement with massive participation, and we use social media, and the media coverage for the Occupy Wall Street was kind of spotty. So we use social media to look back, to reconstruct the events that happened during that year-long movement, and we were able to answer all of these questions through analyzing and visualizing Twitter data that's related to the Occupy Wall Street movement. So some of these questions include: is the Occupy Wall Street movement an organized event, or was it more spontaneous? And how was the movement geographically spread? So if you recall, there was the Occupy everywhere, Occupy Chicago, Occupy Seattle. So there are different particular movement, and who are the key players, what were the major events, and what are some of the public policy related events. So many interesting questions that a social scientist may be interested in asking, and then we can use analysis and visualization to help people answer all of these questions. So my research is really kind of to use interactive visual analysis of textual data to understand social phenomena. So in particular, we produce a combination of interactive visualization plus machine learning methods, statistical and machine learning methods, AI, and we place human. As you can see, human is important. We place human at the center of this problem solving. We actually use the interactive visualization and machine learning to augment human intelligence. And based on the user then will just interact with the visualization dashboard, and they're by no means required to understand what goes under the hood. We don't require our end users to be expert in natural language processing to be able to use our dashboard, right? We want to democratize the visualization and the natural language processing methods to enable everybody, including like business analysts, to be able to explore and analyze the massive amount of textual data and validate the patterns and be able to respond if they want to in almost near real time. So that's our objective: leveraging data analysis and coupling data analytics and interactive visualization. So again, to kind of drive that point home, so I borrowed a a figure from Ben Schneiderman, which is a very famous researcher in HCI. So we're now almost at he called it a second Copernican revolution. So it used to be like the AI is in the center, human just facilitate AI, but now I think our mindset, being our research field in visualization and HCI, is we want AI place human in the center, human in the loop, while using AI, any AI, to facilitate human decision making. So that's our kind of stance. And to give you a couple of examples, so we actually started this line of research a while back, almost 10 years ago, that we started to analyze the impact of scientific funding, right? So we started analyzing, extract topics and time, temporal patterns from research submission, research proposals. So that's one example, like funding agencies like National Science Foundation need to examine the impact of their funding strategies and science policies. But it's difficult to look into the topics, the actual textual information. Most of the time, they rely more on more quantitative information, like how many students were supported, how many research publications were generated out of that award, right? So we want to equip the program directors to analyze full texts of the full text in terms of proposals and publications as results of the funding, right? So the challenge is, well, how do we help them without requiring them to be an expert in natural language processing? How do we help them to analyze the impact of the funding, right? So this, to give you an example, that this is one of the data collection. We visualize a small data collection. That this is the publications on visual analytics, science and technology.
Dr. Dou, let me interrupt for a second. Your screen is not updating. Could you advance the PowerPoint to the section where you're speaking?
Yeah, so are you seeing the visualization?
We see the title screen.
Oh, you see the title screen? Oh. Well, okay, so now are you seeing
We now see temporal depiction of corpora.
Oh, okay, maybe I'll do it this way. So when I did play, but thank you for letting me know. As it will be helpful if you can see the visualization while I'm talking about something.
Certainly, right.
Yeah. And so in this case, we're analyzing the impact of funding program. So we, as you can see, in this visualization, time runs from left to right, and we're visualizing the major trends in scientific publications. And as a user might go through this visualization, the volume has to do with the number of publications that related to a particular topic. And when we have an expert exploring this visualization, he actually identified two rising topics, meaning the topics get thicker. So there's more in the recent years, more publications in the recent years that focus on that particular topic. And we were able to identify a trigger for that pattern. So it was because of a particular program from the National Science Foundation that's called Foundation of Data and Visual Analytics. So, and because of that funding program, and as a result, more research publications are in the field of visualization are related to.
Dr. Dou, I hate to interrupt again. Can you switch it to presentation mode because we can't read the text?
If I switch, can you see the screen? Can you see the temporal depiction of corpora, or are you seeing?
We see the screen, but we can't see the text in your text boxes.
Oh, sorry, I'm having too many trouble. Let me share my whole screen. So I'm not sharing just an application, but if I share the whole screen, that might solve the problem. Okay, how about? now.
It's still okay, but much better. Right. That's much better.
Okay. So
So,
now
okay.
go to a different visualization. So now we're looking at a visualization we generated for the Occupy movement. So this is we developed the visualization on our own based on the analysis method we run on all the social media posts we collected that's related to the Occupy movement. Again, on this visualization, time runs from left to right, and you can see this is the starting point of that official start of the Occupy movement in September 17th, 2011. And then it's a year-long movement, right? Our visualization ends at September 17th, 2012. So, and with this, and then the volume has to do with how many tweets. The height has to do with how many tweets are related to the Occupy movement. And based on this, just the temporal trend, we were able to kind of divide the movement into a couple of stages. The first one is precursor, so we can actually detect like organizing activities on Twitter before the official start date, before the very first movement, before the very first protest. And you can see we have all these activities going on Twitter. These were, we call it an outbreak rapid development stage of all the protests. And after the new year of 2012, you can see the kind of the volume related to the Occupy movement subsided significantly. So all of that can be observed. And also there's in May 2012, there was some effort to trying to revive this movement, but based on the volume we saw from Twitter, it was fairly unsuccessful. There was a slightly bigger peak, but then it wasn't, people's attention have moved on Twitter to other events, right? So, and so that's just the overall pattern we can see overall where like during these few months, 3 to 4 months, people are really interested in the Occupy movement and they are tweeting related to Wall Street. And in terms, and the different color are related to different kinds of topics. Some topics are related to media coverage, and other topics like the orange one over here is more related to kind of the interaction between police and the protesters. So we can, so these, the dashboard is interactive. In the interactive version, you can actually click on a particular topic. And so this is one topic, and we'll show you kind of individual event within that particular topic. So that turns out to be very useful for kind of more detailed analysis. And but also taking a step back, there's we also want to highlight the geospatial aspect of it, right? We detect the places mentioned in the tweet, and then we were able to construct over time what are the geo hotspots. So initially, while the most I guess popular hotspot is the New York City. That's where the first protest occurred. But you can see around the country. So this is just within the U.S. There's also international event. We just didn't plot the international plotted on the international map. But you can see within the U.S. there's Occupy Wall Street, but there's also Occupy Seattle, Occupy Oregon, Occupy Oakland, Occupy. So there are different geospatial chapters that people are organizing on the ground. So that's the geospatial pattern we got from analyzing also Twitter. And more interesting, there's also the precursor. If you know Twitter, most of the tweets are public. You can actually see what the organizing activity. So before the official start date, the September 17th hashtag, the Occupy movement, OWS, Wall Street, that hashtag, they were created way before, a few months before the official start date. So there was kind of a systematic organizing effort on Twitter that we can find. So that was sort of a retrospective analysis of the Occupy movement after the event have occurred. We can collect information from Twitter and then help social scientists, people like social scientists, to answer, to explore data and answer some of the hypotheses and research questions that they have. But what if we want to look at, because more activities are now organized on Twitter or on other social media, can we detect, identify future events? So the answer is yes. So we actually created another interface. We call it the crystal ball. So this is to help people to sift through Twitter, but to discover future events that are currently being organized, and then we plot them. So this is time, in terms of time, when is it gonna occur, where is it gonna occur, what the event is about, and then the social network, possibly which group or groups are organizing the event, and also individual tweet to help you understand what the event is about. Right? So that's something we've also done, leveraging both kind of natural language processing, machine learning, as well as interactive visualization. So the final dashboard is a visualization that any user without kind of any data science background can go in and explore a large amount of tweets or other textual resources. So with this, so that's more on the application side, right? But we want to use it to study how, because the interface, the dashboards are designed to augment human intelligence. But we also want to study when we, as users, when we use the dashboard like that, or any dashboard, to solve a problem, or what are the potential kind of biases that might stem from the human side, stem from our side. So this is to borrow a image from Jeff Hare's keynote talk at 2019 Euroviz. So the title of that talk was "Visualization is Not Enough." So there were so many point of failures that could happen, like in the data science pipeline, from data collection all the way to visualization. And in our case, we want to use the interactive dashboard that we designed to analyze where kind of user could exhibit kind of cognitive biases, like confirmation bias, that we are trying to look for evidence that confirming our prior evidence, or another cognitive bias that we all exhibit is anchoring bias, that we tend to focus too heavily on one piece of information when making decisions, right? So this could be, this happens to everybody. So we could enter, well, one example is when you anchored on the suggested sales price at the gallery, when you purchase art, or when you go to purchase a car, you are anchored at that MSRP. So you're anchored at that price. You, most of us are less likely to cut it in half. So because we're anchored on that one piece of information, then we just adjust slightly away from it, but not too much. So anchoring bias occurs everywhere, and it has been widely studied in the psychology literature. So what we want to see is whether anchoring bias transfers in a visualization setting when we use a visual dashboard. So all of these studies were done without kind of visual visualization dashboard. So all of these are based on maybe just textual information or tables, but what we want to see whether people can be visually anchored. So when we use a dashboard like this, could user rely too heavily maybe on the geospatial information, or too much on the temporal information? Is it possible for user to do that? And what are the consequences if they do rely just on too much of only one part of the dashboard? So that's our two visual anchors. One is the timeline view, we call it temporal. The other is spatial, we call it a geo or spatial anchor. And then we also have a numerical, we use that interface. And then our the task we ask our users to solve is, do you think the number of protest events in the state of California was higher or lower than a certain number? So this was more traditional numerical anchor studied in psychology. So that was a task. For one group, we give them 152. For another low anchor, numerical anchor group, we give them number 8. And we just want to see whether that has an impact on their final answer, right? So that's our task. and these are our research questions. And we did find in our visualization, if people are anchored on a geospatial view, then they did spend significant amount of time. So this is the amount of time they spend on the map view. And then if they're anchored on the timeline, they will spend significant more time just leveraging the timeline, right? So people can be visually anchored, sometimes just by familiarity of a visualization. And the numerical anchor definitely has a huge effect. If we say, is the number of protest events going to be higher and lower than 8, then the average final answer for that group is 21 protests. If we say higher or lower than 152, that was in our question, then the answer, the average answer for the protest they can find is 52.7. So this doubles the amount from the other group, right? It doubles the number, more than doubled, so almost triple. So this, the numerical anchor, the way we frame our questions, also has a huge impact on people's answer, especially with an exploratory task like this. So the answer is yes, we were able to find all of these kind of anchoring effect in decision making, leveraging like a visualization dashboard, and we were also able to detect, based on their clicks and hovers in the visualization dashboard, we were able to find systematic differences in their interaction patterns and information seeking activities. So this finding is very interesting, and that led us to want to know more about what's kind of biased behavior when people are exploring in the dashboard, in a dashboard like this or in a dashboard like Tableau. So if we know people are exhibiting biased behavior, can we possibly intervene with AI? Can we give people a nudge so that they exhibit less cognitive bias, right? So that's just some interesting future work we'd like to pursue. But coming back to summarize the talk, so my research focuses on interactive visual analysis of textual data, and you can see it's very applied. We've worked with many companies to look at their social media presence. We've worked for government agencies to kind of collect social media data to inform public policy, like the COVID pandemic. I think visualization played a very important role in educating the public about different issues related to public health, right? So so our work in that sense is very applied. We want to study how do we best convey the message based on the data, and we also I guess the third part of my presentation was about we leverage a dashboard we designed to study kind of cognitive biases in decision making, because we want to enable people to make decisions, but we also want to make them aware of potential biases in their decision making activities. So, and there are many interesting future work that can come from this. Okay, so. I thank you all for listening. I apologize about the first part that the slides weren't advancing, but hopefully you got to see the visualizations in the second part.
Thank you, Dr. Dou. Very entertaining presentation. There are no questions in the Q&A, but I do have one of my own. Do you see these online events that occur spontaneously? Are you able to profile them, or is every event unique?
So what with the future events? That's an interesting question. So the events we were looking for, well, they do some do share characteristics, right? So if you think about Twitter, most of the tweets are about current ongoing events. So looking for signals on future events, that's almost like looking at the very, very small subset of tweets and with a lot of noise. And we do find a lot of commonalities. So for a lot of the events, if it's crowd gatherings and things like that, and protests, they will have a physical location. So what we were looking for at the time with the crystal ball interface was we were looking for a location that occurred statistically together with a future date. So that's, and then we'll kind of verify that with an algorithmic approach from there and visualize the signals that we found. So we were displaying that the events with a physical location. But there are also other events that's sort of virtual right now. So that's a different group of events. But there's also ways to kind of cross validate the time. Some of the events people registered on the event list, so you can actually get to cross-reference Twitter with other kind of event registration site like Eventbrite, so that to make sure some entertainment events are advertised well beforehand. So it's interesting, but we are also interested in those events that are more kind of crowd gathering and protest like events.
Oh, thank you very much again. Our next speaker is Gabi Zodik. Gabi has a master's and a bachelor's in electrical engineering from Technion, master's from the University of Haifa. He'll be talking about blockchain and the myth and promise. And he manages the blockchain and IoT technologies department at IBM Research. Mr. Zodik, go ahead.
Thank you. Let me share my screen and presentation. Okay. Can you see my presentation?
We can see it.
Okay, excellent. Thanks for having me. And yes, I welcome questions. I'll give a brief overview really of the research we are doing at IBM in the area of blockchain. We have multiple research teams across, I would say, Europe and Asia. And we've done multiple contributions to our open source project, Hyperledger Fabric, which is our blockchain platform, in multiple areas around security, consensus algorithms, and so on. I'll describe some of that work in a little bit more detail. We also work with multiple clients to get more requirements and look into future direction of the industry. And I'll mention some of those examples as well. And we also look at new paradigms of blockchain, such as new centralized approaches that extend database kind of technologies with blockchain characteristics. So just in a nutshell, many people attach blockchain with cryptocurrency, certainly with Bitcoin. So just to level set, the main interest we have in IBM is primarily around permission-based blockchain networks. So not public networks such as, let's say, Bitcoin or others, and not necessarily around cryptocurrencies. You'll see that we do have interest in currencies, but usually these are utility currency or digital currency, as we'll speak in a bit. Now, with permission-based network, there are some common concepts. Essentially, the network or the blockchain technology really provides trust among the participants. And the participants are well known. They have a business contract. It could be a set of banks in a country that have some business process running across them, or companies, or a mix of those. Could be in the logistics space, and so on and so forth. And that we have this common ledger, and there is the provenance and non-repudiation, the fact that everything is cryptographically signed, creates from one end the transparency of this shared ledger. On the other hand, it really increases the trust among the companies, oftentimes creates automation and reduces really third-party entities, formal entities that need to approve transactions, remove disputes, and so on. Nevertheless, what's been done, there is obviously quite ongoing active research in multiple of these directions around privacy and scalability of these systems to really make them scale to the number of transactions that are really needed in the industry. Now, if I move to one of the topics, as I mentioned, is around representation of various assets. And one of the common names that you hear associated with the blockchain is this notion of a token. And again, a token could represent something like cryptocurrency, but it can also represent many other things. It can represent any physical object or share or exchange or sell or have a marketplace. It can also represent, of course, non-tangible, again, of value. Could be digital rights, could be patents, could be any other thing that has a value. And it is really just a very common way to abstract and link the physical world with the digital world. And it's out. And again, we use this, as you can see, in multiple domains and in multiple industries. And we can create, as I said, a marketplace of various assets and so on and so forth. One really example is in that most of the countries in the world and most of the banks worldwide are looking into is into digital currency, central bank digital currency. Now, this currency, unlike the crypto currency or Bitcoin, is driven usually by the central bank, and it's associated with the currency in that country. It is a digital form of the physical form of that currency in that country. And as such, it has a given value. It is something that's trade, and it's something that people certainly can rely on and use in their day-to-day. So the digital, and this is something that all the banks across the world, we are working with some of them, are looking to move in, because as many of us know, like those in China know the use of WeChat and Alipay. I know in Israel we have multiple of the applications, and in a sense we are moving already into that direction. We do many things in a digital form, only that underlying this, we still have the physical currency, which slowly is going, not slowly actually, pretty fast going away. And one of the things is that central banks would lose the control if they won't introduce this digital currency. Now, it's not so easy to introduce a digital currency, and that's why many of the central banks are very progressing slowly with multiple experiments. This list is just, I think, a partial list. Just an example, anonymity from one hand is critical. On the other hand, they want to be able to audit and prevent money laundering. So you already see these conflicting requirements. So while you have a token and I can pay somebody, and that's represented with the token, it needs to preserve the and possibly my anonymity and so on. There are additional challenges like offline. So obviously in multiple cases, multiple countries, we have mobile phones and we're most of the time connected. Nevertheless, we can be in a situation where we are disconnected and I still want to pass or pay someone. And we need all the guarantees that I have to do so. I have the required balances and so on. And just to give another example here of the user friendliness. So obviously many of us know how to use smartphones, but not everyone can use a smartphone. So this needs to be user friendly for whether elderly people or people with disabilities or people in countries where they simply don't have a smartphone or don't have connectivity. So there are multiple challenges, and again, technology can cope with some of these or many of these, but as you see, there are also challenges that go beyond the technology. And again, if you look at the big picture, central bank digital currency sits somewhere in the middle here in the intersection, right? Across several of these known currencies that we have today. One of the additional challenges, I would say, when we would create these networks to run digital currencies is the fact that there will be also multiple networks, even in the same country. So the commercial banks would connect among themselves. If it is a large country, most probably there'll be multiple networks. They may have different representations and abstractions mechanisms that they would implement. And one of the challenges would be these cross-ledger relay protocols or interoperability among these networks. And indeed, it is an area we are looking into and doing a lot of research, because unlike any other system, distributed systems, it's not so simple to integrate among blockchain networks and preserve all the qualities and guarantees that one gets in one network. Then we need also the ability to atomically swap assets, meaning I want to do a transaction in one network, and sometimes that transaction is linked with the transaction in the second network. Let's say I have a network in which I'm ownership of a car to someone, and I want to be paid in the other network. So these transactions now are associated and need to behave in an atomic manner. Only if both of them are successful, like them to be written to the ledger. And if one of them fails, obviously the second one should fail as well. So again, just some of the challenges that still are out there, and there is some work that we are to cope with these challenges. So I mentioned interoperability, and I gave kind of, I guess, a couple of examples. So there are several capabilities we are looking in doing interoperability. I've mentioned the atomic or the asset exchange as an example. There could be also movement of assets, or in that case, could be currency, from one network to another. And then we need all of the guarantees to make sure that there is no overspend, meaning that if I move some money from one network, then the tokens that are representing that will be destroyed, and new tokens will be represented with the exact sum, and no double spend can happen. Or for that matter, transferring data among networks. And again, the challenges here come from the fact, because blockchain creates this trust by this consensus mechanism among the participants, it is not a case where I can just invoke a single API on one of the nodes in the remote networks. It might be a malicious node, so I may not trust it. So I need to get some guarantees that the data that I get back, data that the consortium there of consensus algorithm agreed upon, and it's the data that's written in the ledger. So one of the techniques being used, or oftentimes used, is proofs that are associated with that data to the authenticity and the correctness of the data. It's more challenging than this, and there is an open source project called Weave as part of the Hyperledger Labs. I of course invite anyone interested in the domain to look into this, and of course we welcome participation and contribution. I'm switching gears and moving to another topic, and that's around digital identity. It's not a new area, it's something that's been out there for a few years now. There are multiple drivers to digitize our identities. From a citizen's point of view, the desire is to protect the privacy usually. From government's point of view, it's of course to remove fraud and build more trustworthy systems. Again, it's a slow progress, and multiple countries are introducing more and more of these digital identities. I think one of the side effects of COVID-19 was the fact that there was more need to verify the health status of people, and again, not in general the health status, but really more related to have that person being vaccinated or not, or have he done some test and he's now negative or unfortunately positive, and all of that to be done in a privacy preserving manner to prevent fraud and so on. And this is essentially an example of a digital identity scenario where you have really from one end issuers. So an issuer could be a lab that did a test, or it could be the hospital or any other medical center where somebody did the vaccine, and they would create a certificate for that person if he's been, let's say, vaccinated, and he can carry that certificate. This certificate, of course, is encrypted, and whenever he needs to enter or get on a flight or enter a mall, or whenever he needs to prove that he's been vaccinated, he can pull out that certificate, show it to the verifier, and the verifier can check two things. One, the validity of the certificate, that it is indeed belonging to that person, indeed that he is vaccinated. All of that data can be decrypted from the certificate with a public key. But the second thing he can verify, and that's the primary use of blockchain in this scenario, that whoever signed the certificate is an authorized authority to sign and create those certificates, let's say by the government. So if a particular hospital created a certificate, that can be verified, and it can be verified that it has all the authority. So two checks can be done. Again, not many countries have adopted this technique. It's pretty simple technology using blockchain, and it's a very nice example of the digital identity. Unfortunately, still many countries just use very simple methods to share this data and not encrypt it and not use certificates. But what it demonstrates, it's the fact that from one end, it can protect the privacy of people and only disclose the exact information needed to the verifier, and those certificates additional data. And of course, verifiers can have all the proofs needed and trust the system. And again, it is GDPR, HIPAA compliant, preserve, as I mentioned, privacy. Let me move on. One of the other areas of work is around consensus algorithms. That's kind of the heart of the ordering service of these permission-based blockchains. And again, it is another Hyperledger lab called MIR-BFT, with the aim to really being able to scale to hundreds of nodes that would run the transaction, and not only run in a LAN, in a close proximity, but can actually run across wide area networks and still perform way better than other existing algorithms. Again, it's ongoing research, and there is an initial implementation, and we welcome more people to join, those who are interested in this field. I've mentioned at the beginning that we're also exploring new paradigms. So initially, blockchain, to create the trust that I've mentioned at the beginning, the basic idea was it is a decentralized system. The fact that every participant in the network can run one of the peer nodes, and the consensus algorithm I just mentioned runs across all the peers, gives them additional trust in the network. One of the observations we've made over the years that we've been working in this space with our clients, including with existing network like Food Trust and TradeLens and others, is that oftentimes the consortium, the set of companies in the network, trust a single entity like the cloud provider or technology provider, such as IBM, or could be Microsoft or anyone other technology provider. And in fact, what we see that in practice, they run the entire network on that cloud provider and don't take advantage of the decentralization capabilities. And they get, of course, all the trust by the provenance and the non-repudiation, all of the characteristics that blockchain provides. Yet they suffer from more complex deployment, more difficult, I would say, or more complex programming model of a distributed system. And one of the direction the industry is going, including us, and Orion is one such implementation, is to existing well-known database programming model and build an additional layer on top of it with the same characteristics as blockchain, which would provide non-repudiation, all of the temper evidence and transactions with the same kind of qualities like a ledger that's non-changeable, and so on and so forth. So it gives the same capabilities as a blockchain, only that it runs centralized on a cloud provider, of course, with replicas to be highly available, and provides a more simple way to deploy, more simple way to program it. So again, this is also an open source project, also in Hyperledger Labs. Again, welcome people to join and look into it more. Let me skip this one, and because I'm running out of time, I'll just conclude with another major area of investment is around data quality. So from one end, we want to do more AI, and certainly with blockchain, when we have these networks, we produce more data. One of the challenges is the privacy of the data, and we do have work around multi-party computation and how that can run in the context of blockchain. The other challenge is more around the data quality that the participants in the network share. And I would just say that one of the areas we are looking at is how to statistically, continuously check the data quality, even improve it automatically if possible with statistically data that we accumulate, as well as to create the correct incentives to the participants to share and continuously improve the quality of the data that they are sharing by monetary rewards and other ways of rewarding. And we are looking at advanced things such as game theory and other means to really see how we can data providers and the data consumers to continuously improve and with that, I think I've reached the end of my presentation, and I'll stop here because I think I'm running out of time.
Thank you very much, Mr. Zodik. I see, I'm not sure if we have any questions. I don't see any in the Q&A. No, there are no questions. I do have one question for what I'm calling thin clients, nodes that do not have the capability of storing the full ledger, Internet of Things devices on the edge. How do you see their implementation in a blockchain construction?
Yes, so we do have a way to cope with that. I did not mention that, in which you can think of sensors even that want to participate in a blockchain network, or very small devices that don't run the client and certainly don't need to, they can't even run the client because they are so small. So one way to cope with that is to run a proxy on their behalf that would run on a gateway, like a Raspberry Pi or something at that size. And that proxy would run the client on their behalf, and the protocol between them and the small device, like the sensor, would be primarily to validate the sensor. Maybe there's some ID, identification, authentication, but the rest of the protocol of the blockchain would be running through a proxy, and that proxy could actually accumulate multiple of those sensors and allow them to participate and create transactions.
So somewhat like a mini node in a star configuration.
Yeah, something.
Okay, thank you very much. We now have a 15-minute break before the afternoon sessions start. So please visit the vendor display, the exhibitor displays, and we'll see you back again here in 15 minutes or so.